Right now, somewhere deep inside the sun, a war is being fought. And every 11 years, one side wins completely. The sun's entire magnetic field flips. North becomes south. South becomes north. And for a few strange days in the middle of that flip, our star doesn't have one north pole and one south pole like it's supposed to. It has two of the same pole at the same time. An arrangement that shouldn't be possible for any magnet anywhere. But here's the part almost nobody talks about. During that exact window, something happens to Earth that most people have never connected to the sun at all. I'll tell you exactly what that is at the end of this video. And once you know, you'll never look at a solar flare, an aurora, or even your phone's GPS signal the same way again. Today we're going deep into the sun's magnetic heart, how it builds this tension, why it always breaks every 11 years, and what that means for the world you live in every single day. Hey, welcome back to Cosmic Story Lab, the channel where we take the universe's biggest mysteries and make them make sense. Let's get into it.
Here's something that surprises a lot of people. The sun isn't solid. It's not rock, it's not metal. It's a churning ball of superheated, electrically charged gas called plasma. And when you take electrically charged material and spin it, you get something powerful, a magnetic field. But the sun doesn't spin like Earth does. Earth rotates as one solid piece, top to bottom, all at the same speed. The sun cheats. According to NASA, its equator spins faster than its poles, completing a rotation in about 25 days, while the polar regions take closer to 35. That's called differential rotation, and it's the whole reason this story exists. Picture stretching a rubber band around a spinning ball, where the middle spins faster than the top and bottom. Over time, that band doesn't stay neat. It wraps, it twists, it tangles into knots. That's exactly what's happening to the sun's magnetic field lines, month after month, year after year, winding tighter and tighter and tighter. And that tension has to go somewhere.
So why does this tangled mess resolve itself on an 11-year schedule, almost like clockwork? Scientists call this engine the solar dynamo, and researchers at NASA and various universities have spent decades trying to fully model how it works. As the magnetic field lines twist tighter beneath the surface, they occasionally punch through, creating dark, cooler patches we call sunspots. Sunspots are where this whole story becomes visible. Early in a cycle, sunspots appear near the sun's mid-latitudes. But wait, as the cycle progresses, they don't stay there. They gradually march toward the equator, like an invisible clock counting down to wind. Astronomers even have a nickname for the pattern sunspots make when plotted over time: the butterfly diagram, because it looks like a pair of wings unfolding. When sunspot activity peaks, we call it solar maximum, the moment the tangled magnetic field can't hold together anymore. And right around that peak, the entire field breaks and reorganizes itself, flipping polarity completely. It's not random. It's the release of built-up magnetic stress over and over, roughly every 11 years. Here's the twist though. 11 years only gets you back to a similar sunspot pattern. The magnetic poles themselves don't return to their original arrangement until two full flips have happened. That's called the Hale cycle, and it actually stretches across about 22 years. So in a strange way, the sun's true full magnetic day is double what most people think.
Now here's where it gets genuinely strange. Right around solar maximum, NASA's Solar Dynamics Observatory has captured something that shouldn't make sense on paper. For a short period, different regions near the poles can show mismatched, inconsistent polarity as the old magnetic pattern breaks down before the new one fully takes hold. It's not a clean, instant swap. It's messy, chaotic, and it's exactly during this chaotic window that the sun tends to throw its biggest tantrums. Solar maximum is when sunspot numbers peak, and it's also when solar flares and coronal mass ejections become far more frequent and far more powerful.
These eruptions send bursts of charged particles racing toward Earth at incredible speeds. When they arrive, they slam into our planet's own magnetic field, and that collision is what fuels geomagnetic storms. And this is the part that connects directly back to what I promised you at the beginning. During these post-flip storm periods, Earth's upper atmosphere actually heats up and expands slightly. That expansion increases drag on satellites orbiting close to Earth, which is why space agencies have to occasionally nudge satellites, including parts of the International Space Station, to keep them from drifting off course. So that flip happening 93 million miles away, it reaches all the way up into the machines orbiting right above your head. The same storms are also responsible for auroras appearing far outside their usual polar homes, and for radio and GPS disruptions that ripple across the planet. None of it destroys civilization, but it's a quiet, constant reminder that our calm, reliable sun is really a slow-motion magnetic storm, resetting itself again and again, forever.
So there it is, the answer I promised you. That impossible moment when the sun briefly loses its clean magnetic structure isn't just a curiosity. It's the exact period when Earth's satellites face extra atmospheric drag, when auroras wander toward the equator, and when our technology gets its biggest test from 93 million miles away. If this made you see our closest star differently, that's exactly why we make these videos. Hit like if your brain just got a little more expanded, and subscribe if you want more of the universe explained in a way that actually makes sense. If you're curious what happens when the sun's tantrums get even bigger, go check out our video on the most powerful solar storm in modern history. You won't believe what it did to farms, flights, and satellites in a single week. Here's a question for you to sit with. If our own star is this unpredictable, what does that tell us about the billions of other stars out there we've barely even studied? Drop your thoughts below. I read every one.